Hello, the discussion is on dual nature of matter. Session 8, Heisenberg uncertainty principle and its application. Recap, there is a relation between group velocity and phase velocity and a relation between group velocity and particle velocity. Now the relation is what Vg is equal to Vp minus lambda into dVp divided by d lambda, where Vg be the group velocity, Vg is equal to d omega by dk. It is the velocity of group of waves present in a wave packet. Then Vp is equal to phase velocity. In a wave packet, each wave moves with a particular velocity called wave velocity or phase velocity. Then another relation is group velocity and particle velocity. The relation between them is Vg is equal to V. That means group velocity is equal to particle velocity. Then learning objective. The objective is to study the Heisenberg uncertainty relations and illustrate this Heisenberg uncertainty relation in the case of gamma ray microscope. This is an experiment related to the gamma ray microscope. Then session outcome, the students will able to understand the Heisenberg uncertainty relations and illustration of Heisenberg uncertainty principle. Prerequisites, gamma rays. Gamma rays are the electromagnetic radiations of wavelength 0.001 angstroms to 0.1 angstrom in it. It is not deflected by electric as well as magnetic field. Its speed is 3 into 10 power 8 meter per second. And the gamma rays, its wavelength is very less, therefore the resolving power is more. The resolving power of a microscope, second term, it is the reciprocal of limit of resolution, and an expression for resolving power of microscope is 2n sin theta divided by lambda. N is the refractive index of the medium, theta be the semi-vertical angle when the cone of rays entering from objective to objective, lambda be the wavelength of light used. Limit of resolution of a microscope means it is the minimum distance of separation between the two closely lying point objects which are just seen separately, and limit of resolution symbol dx, that is equal to lambda by 2n sin theta. It is the reciprocal of resolving power of the microscope. Then Heisenberg uncertainty principle. According to classical physics, if the initial values of position and velocity as well as momentum are known, then it is possible to calculate the momentum as well as velocity and position of the particle exactly. But that is not possible according to quantum mechanics. If position is measured accurately, it is not possible to measure momentum accurately. Then using this idea, Heisenberg gave a relation as well as statement that is called Heisenberg uncertainty principle. The statement of this is, it is impossible to measure the position and momentum of a particle precisely and simultaneously. If one is measured exactly, then that is not, the position is measured exactly, the momentum is not measured exactly. There is an uncertainty in the measurement of position and momentum. Taking into consideration the three conservation laws, the uncertainty principle is stated mathematically like this. One is delta x dot delta px is greater than or equal to h cut by 2, where delta x be the uncertainty in the measurement of position, delta px be the uncertainty in the measurement of momentum. Then according to Heisenberg uncertainty principle, delta x dot delta px is nearly equal to or greater than or equal to h cut by 2. Similarly, delta L be the uncertainty in the measurement of angular momentum, delta theta be the uncertainty in the measurement of angular displacement. Then according to Heisenberg uncertainty principle, delta L dot delta theta is also greater than or equal to h cut by 2. Similarly, delta E dot delta T greater than or equal to h cut by 2. This is the third Heisenberg uncertainty relation. Delta E with the uncertainty in the measurement of energy, delta T with the uncertainty in the measurement of time. So in this way, three uncertainty relations are formulated. The three uncertainty relations are delta x dot delta px greater than or equal to h cut by 2, delta L delta theta greater than or equal to h cut by 2, delta E dot delta t greater than or equal to h cut by 2. If delta x be the uncertainty in the measurement of position along x-axis, delta py be the uncertainty in the measurement of momentum along y-axis, then delta x dot delta py is equal to 0. Similarly, delta y delta px is equal to 0. Delta L delta theta greater than or equal to h cut by 2. That means you measure position and momentum in the same direction, then Heisenberg uncertainty principle is valid. The experiment is used to explain the gamma ray microscopic experiment. So according to this, we know the resolving power of a microscope. It is the resolving power of an optical instrument means it is the ability of the instrument to see two closely lying point objects separately. Resolving power of the microscope is the reciprocal of limit of resolution. Limit of resolution means it is the minimum distance of separation between the two closely lying point objects that are just seen separately. The expression for limit of resolution of a microscope is delta x is equal to lambda by 2 sine theta, where theta be the semi-vertical angle when the cone of gamma rays entering from object to objective. Delta x be the uncertainty in the measurement of position, lambda be the wavelength of light used. Here the wavelength of gamma rays are used. Then come to the uncertainty in the measurement of momentum, because we measure uncertainty in the measurement of position delta x as lambda by 2 sine theta, n sine theta actually, but 2 sine theta because in the case of air medium n is the refractive index of the medium, air it is 1. Therefore delta x is equal to lambda by 2 sine theta. Now a beam of photon incident on an electron at O, then x momentum component of momentum of the photon scattered in the direction of OA is h by lambda into cos 90 minus theta, that is h by lambda into sine theta. The x component of momentum of the photon scattered in the direction of OB is minus h by lambda into cos 90 minus theta, that is minus h by lambda into sine theta. Then momentum transfer to the electron by the photon scattered in the direction of OA is P naught minus P, that is P naught minus h by lambda into sine theta. Momentum transfer to the electron by the photon scattered in the direction of OB is P naught minus P again, P dash will be called as P naught minus of minus h by lambda into sine theta. The minus into minus plus, then P naught plus h by lambda into sine theta. In the experiment, the momentum of the electron lies between P naught plus h by lambda sine theta and P naught minus h by lambda sine theta along x-axis. Then the uncertainty in the measurement of momentum delta px is the difference of these two, P naught plus h by lambda sine theta minus P naught minus h by lambda sine theta. If you simplify this, P naught gets cancels, h by lambda sine theta minus of minus plus h by lambda sine theta, that is 2h by lambda into sine theta. Then we know uncertainty in the measurement of position along x-axis is delta x is equal to lambda by 2 sine theta. The uncertainty in the measurement of momentum in the x direction is delta px is equal to 2h by lambda into sine theta. Then delta x dot delta px is equal to 2h sine theta by lambda into lambda by 2 sine theta. 2 sine theta gets cancels, h gets cancelled, that is equal to h, which is the Heisenberg uncertainty principle.